Hello viewers, in this video we'll go through Cambridge A-Level Further Maths Component 2 Variant 1 from the 2025 October-November series. In this video we'll go and attempt question 7. Okay, this question 7. First part, they want us to show that this derivative is true. So if you go ahead and see your, what we call it, the formula list, you can see that actually there is a formula for this, right? But obviously you're if you use that, you will not get any marks here because they want you to actually show how you get or the derivation of this expression. So what I'm going to show you is to do it using the implicit differentiation. Implicit differentiation. Okay, so first let's assign this inverse tangent as a variable, let's say y. So let's say y is our inverse hyperbolic tangent of x, and therefore we know with this also that you can get that x will be the hyperbolic tangent of y. Okay, so this is just the inverse property. And now if we go and differentiate this tangent hyperbolic of y, we know how to differentiate. We can use some other formula here. So which is this one. Okay, so if we take the derivative d dx of x, and on the right hand side I also have to take the derivative d dx of hyperbolic tangent of y. But in this case, right, because our variable of this hyperbolic tangent is in terms of y and our operator is in terms of x, we need to do something called the chain rule. So we need to multiply it by or not yet, okay, because we want to what we call differentiate in terms of y for this one, we replace this dx with dy. Then to get back the dx, we have to do the chain rule. We multiply by dy dx. Right? In this matter, the the dy and the dy, they can both cancel out, and you're left with just a dx. So this is how you do the what we call the implicit differentiation. So this hyperbolic tangent of y, you can differentiate as usual in terms of y. So we will get, what was it? The hyperbolic secant of y. Okay, hyperbolic secant square of y. And this dy dx, it just remains there. So dy dx. So like that. And on the left hand side, the derivative of x is just 1. So now we have, yeah, we can try to isolate dy dx on one side, which will get this one. 1 over hyperbolic secant square of y. Okay, up to here, what we can do next is we will use one of these the identities, right? So this Pythagorean identity of the hyperbolic cosine and hyperbolic sine, it will be equivalent to 1. So if we divide both sides by the hyperbolic cosine squared, you get 1 minus tangent squared will be equal to or equivalent to the hyperbolic secant squared. So again, what I said, 1 minus tangent hyperbolic square, right? So this one we can actually replace with 1 minus hyperbolic tangent squared of y. Okay, up to this point, we have shown or we have gotten into this form, but we want, actually the question wants us to present in this form. So where the d dx of this, which is dy dx, is the 1 over 1 minus x squared. And if you try and notice, what we have here, we've established at the beginning that x is equal to the hyperbolic of hyperbolic tangent of y, which appears here. So what we can replace this with is just 1 over 1 minus x squared. And so yeah, this will be the end of our derivation, and we can just write that this is shown, right? It's exactly the same. And we'll move on to the second part. Now we want to or they're giving us this differential equation, and with this condition of the domain and this boundary condition, and we want to find the exact solution to this differential equation. So it's kind of in the form where we can reduce it to a linear first order, right? Linear first order ODE. So if you can recall, the first order ODE appears as this type of form where you have a differential term here, then you have a px multiplied by y, then equals another function q of x. And so what we can do in this form is that we divide both sides, divide it by x. So on my left hand side, I will just have dy dx minus y over x, then x hyperbolic tangent inverse of x. So now we reduce it to the first order ODE form. How do we solve it? Is by using this, what we call the integrating factor. I think mu of x will be e to the power of the integral p of x dx. So the p of x, that will be the function here. In this case, there is our p of x, it will be negative 1 over x. So it's whatever coefficient of the y, we take it as our p of x. Alright, and then we'll find our integrating factor. It will be e raised to the integral of negative 1 over x dx, which will get e to the power of negative natural log of x. Now, I do not include the arbitrary constant here because it's not needed. I'm not so sure why, but when we will deal with the arbitrary constant after we finish the whole integration. But in this case, we can reduce this to 1 over x, right? This one, this negative ln x, I'll take this negative to the power of x, and the e and the natural log, it will cancel out each other. So, okay, that's our integrating factor. So actually, how do we use the integrating factor to try and solve our linear first order ODE? We multiply, actually, I'll just rewrite the arbitrary form of the first order ODE first again. And we multiply this mu, the integrating factor on both sides, right? So we have this. You can try and realize that if you expand out this bracket, it will look something like x dy dx and mu of x pxy. And this pattern looks kind of familiar, which is the product rule. So if I have a product of let's say I want to take the derivative of mu of x multiplied by y, where mu of x and y, they are both 2. Right? So mu of x, I leave it and I differentiate y. Then I differentiate mu of x and I leave y. Because mu of x, we already define it to be this form here, and if derivative, you just multiply by px. So yeah, it will be equal to whatever function and multiplied by the mu of x on the right hand side. So what I will do is I will replace I'll do that for our particular equation here. So I'll erase this first. And I'll multiply both sides by 1 over x, right? That is our mu of x. So I'll multiply here, and I'll multiply here. So what we have on the left hand side, again, as I said, it will be reduced to the mu of x, which is 1 over x times y. So actually y over x. Then it will be equal to this one on the right hand side. So now all we have to do is just integrate both sides. On the left hand side, it will be integrated in terms, well, I mean the differential term here is y over x. And on the left hand side, we integrate, on the right hand side, sorry, we integrate with respect to x. There's the dx, it goes to the other side, right? So here, what happens is just, on the left hand side, it just goes y over x. And on the right hand side, how do we integrate this? You can try and find your formula sheet, it doesn't exist. I mean, the information to integrate this doesn't exist. So what we have to do is use the integration by parts. So if you can try and remember the formula, if you integrate u dv is uv minus v du. So we have to choose what is our u, what is our dv. And one we would differentiate, the other we will integrate. So we always choose dv as the one that is more difficult to integrate. In this case, we can take it as like 1 multiplied by hyperbolic inverse tangent. So hyperbolic tangent inverse, that is the one that we don't know how to integrate. So definitely we cannot put it as the I. So we put it as the u, so that we can differentiate it and use the result from the previous part of the question, and dv we just put as 1. So we integrate this, v becomes dx, and this we take the derivative, du becomes 1 over 1 minus x squared dx. So the way I rearrange this, it makes it easier so that you can do the cross multiplication and then you multiply the row here. So this is our result for the integration by parts. So maybe I'll write downwards here. Go down here, y over x, it will be equal to uv x hyperbolic inverse tangent of x and minus the integral of v, which is x dx, and the dx is not supposed to be here. The dx is already down here, so here there's no dx. Okay, so then over 1 minus x squared. Okay, so that's v du here. Okay, up to this point, this is something that we can try and integrate using some other technique, which we call as the substitution. Which also it looks like we can try and identify here, right? The x is a derivative of x squared, so it's something like the derivative of the function over the function itself. So we can try and let u be equal to the bottom function, which is 1 over x squared, and so du will be negative 2x dx, and dx, or isolate dx so that we can substitute in there, it will be equal to du over negative 2x. Okay, now I will copy down everything as before, but only the integral I will change it to be, so x I remain the same, the one on the bottom 1 minus x squared, that we assign it as u, then dx we replace with du over negative 2x. Okay, so this x and x cancel, and the 1 over negative 2 we can take it out of the integral because it's just a constant, and then the negative multiplied by negative 1 over 2 becomes 1 over 2. Okay, so running off space here, y over x, x inverse tangent of x plus 1 over 2 integrate 1 over u du. So 1 over u du is something we can definitely integrate. It becomes the natural log, right? Natural log of u, and u we got as this one already. So we can just directly write down here, and the integral, you turn it to 1 over 2 natural log of 1 minus x squared modulus. Alright, so up till here, now we've finished all the steps. So as I said, now we can deal with the constant of integration. So we just add up. Okay, so now we will make use of these boundary conditions. Y of 1 over 2 is equal to 0 to get our, so y is 0, so the whole left hand side is 0. Now this hyperbolic inverse tangent is in your formula sheet, right? So here, so we just have to use this result to try and get, or try to compute the answer. So x is 1 over 2, and this hyperbolic inverse tangent is 1 over 2 natural log of 1 plus 1 over 2, which is the x, 1 minus 1 over 2, and then 1 over 2 natural log of 1 minus 1 over 2 squared, then plus c. So c will be the negative of whatever the whole thing of this is. So c will be negative 1 over 4 natural log of, this becomes 3, and here also it will also be minus, right? Minus 1 over 2 natural log of will be 3 over 4. Okay, so now I want to get rid of the power. So I'll raise this to power 1 over 4. I'll take it to the top. So the negative 1 over 4, it will become the power. So it become ln 3 negative 1 over 4 plus natural log 3 over 4, and this whole thing becomes 1 over 2, negative 1 over 2. And yeah, so okay, we can simplify this further. You can multiply both of the natural log, whatever is inside the natural log. So 3 power negative 1 over 4 and 3 power negative 1 over 2, 4 power negative 1 over 2. Yeah, these two you add together, right? So yeah. ln 3 negative 1 over 4 plus or minus 0.5, so negative 3 over 4. Then this becomes 1 over square root 4, which is half, so 1 over 2. Or actually they want it exact form, right? Yeah, they want it in the exact form. So yeah, I just rather leave it like this. So ln 3 sorry. So the 1 over 2 I can simplify further. 2 times 3 negative 3 over 4. So actually you could have just left it like this, but I chose to simplify it. I think too much. So finally we can write back the answer. The whole thing together with the arbitrary constant that we found. So plus natural log of 2 times 3 negative 3 over 4. So yeah, okay, this will be the final answer. Okay, so that is question 7, and stay tuned for more videos.